Jackie. Did you hear what she just asked them? She said, if soap drops on the floor, is the soap dirty or is the floor clean? It's a really good question. I don't know the answer to that.
Is the soap dirty or the floor is clean?
Mm-hmm.
I think soap is dirty. No, the soap isn't dirty. The floor should be dirty.
But is the soap, your choices are, is the soap dirty or is the floor clean?
Soap dirty?
I don't know if there's a right answer. There it goes. It's like struggling with me here. It's a good question. It's like with the lab rats a week or so ago, we argued about is water wet?
It is wet.
Is it wet or does it make things wet?
It makes things wet and it is wet.
It's wet. So if you touch the water, is the water wet or now you wet?
I am wet.
It's a good one, right? When you think about it, it's like, uh-oh. And it's like, is a fish underwater? Is he wet when he's underwater or is he only wet if he comes out of the water?
He's wet when he comes out of the water.
But is he wet when he's swimming in the water? I love it. Oh, there's my red-bellied woodpecker. You see him on my feeder?
Oh,
He's a big guy. He's silly.
no, he flew away.
Yeah, he'll be back. He chases everybody else away. That's his favorite thing to do. Scare everybody. House finch. Female house finch.
I can't practice basketball without the rain. Same.
Good morning. How are you?
Are you feeling better?
Yes, thank you. I still have a little cough because my cough reflex is irritated, but not really sick anymore, thank goodness.
Same. I can't warm up outside.
Yeah, I get like every time I eat, I cough. Cause it like, you know, it makes like post nasally stuff and then it triggers like my little cough reflex and I just start coughing. I'm still having for breakfast. It don't matter what I eat, it's just what it is. But it'll go away. It just takes time, you know. I was fortunate it wasn't so bad. Jason got really sick. Like he was all sick. So
Is he feeling better?
yes, he's feeling better, but he has asthma. So anytime he gets sick like that, it's hard for it. Yeah, it takes him a while to get better. Like takes him a little longer to heal.
Mr. Jason is feeling better.
Yeah, he's upstairs, but he's had to like do some breathing treatments and stuff. Just to make it so that he can breathe a little better. Yep. Good morning.
Started this game in this thing in all the Rainbow Park.
Okay.
Yeah, and we
Do it.
won.
You want basketball? Very good.
I practice basketball. I just signed up for
Good job.
it.
Iris is trying to squeeze behind you. There she goes. She did it. They never leave. This is for her. Oh, are those mine?
Yeah.
Thank you. I'm excited. Woo-hoo. You gotta have a dealer.
Yeah, I know, right?
I had a dealer for years and she was a great dealer.
Uh-huh.
And then as soon as BSA opened to girls, she swapped over.
There's
Oh.
no hole in this.
Oh, yeah, I'll get out the whole country.
Oh.
So I lost my dealer and I was real disappointed. So now I've had to get other dealers since then.
Yeah, here we are.
Yeah,
we couldn't resist. We had to open up the s'mores. Had to share.
that sounds awesome.
Yes.
It's a hole puncher, but for some reason. I'm getting a little bit of paper stuck in this one hole and it doesn't want to go. Really gets your undivided attention for the next 2 weeks, I'm sure.
Yes, she does.
There we go. The middle one, I'm punch. What is happening? Yeah, sort of, you got a little extra roll up top now. Whatever. Just wanted to fight with me, I think. Just cause it could.
Like how the ball, like I have to chase, like how when I miss the shot, I have to, in basketball, I have to chase the ball to the other side of the court.
Oh, you play basketball too?
I just practice,
Uh-huh.
I signed up, but
You know Eunice plays, right?
I did not know that before.
Yeah, both Eunice and Yusuf play basketball.
Yeah,
We found,
we play in Old Atlanta.
Mm-hmm.
I did a 2v2 with these two, with this brother and sister and their mom, and I was on the sister's team, and
Okay.
we won 6-2, and I think I made all the shots.
Oh my goodness, and you know Miss Jackie's son is really good. He plays basketball too, and he's really good.
So
On the last side, I think.
Uh,
Old Atlanta play.
I brought Valentine's Day back for everyone.
Oh, look, she's got treats for everybody. Do you want to just put them here? I'll
Um,
hand them out. You hand them out.
Yeah, thank you.
I'll leave them.
Valentine. Have you gotten a Valentine before?
Oh, yeah.
There you go. I was
I
gonna
do
say.
that every year.
That is very
Yeah.
sweet.
I also do that. for
Yeah,
cards.
you're gonna need to get two for the extra students. I'm gonna
Yeah, oh, let me take those.
Make
I told
sure-
your mom that I would hold on to them for you.
make sure all the seniors get one
I
too.
will, thank you. These are Lucas and Xander, because they are not here. Let's leave one for Lucy, because she's coming. Thank you, Annabelle, that's so sweet of you. What a nice girl you are. What a very nice girl. Yeah, these are Lucas and Xander, they're on vacation, so we'll hang on to them for them. One of the joys of homeschooling.
Cards every year.
Your Christmas cards were really sweet. I love that. That is so nice of you guys. I used to love that when I was in school. We would do on Valentine's Day. Everybody would like prepare days before. The teachers would have everybody bring in like a shoebox, or they'd have some kind of a project where you'd make some sort of like a box or an envelope, and you'd craft it in class, and then everybody had to make Valentines for everybody. And then they had to bring them, and you had to pass one out for everybody in class, and it was always fun, because some people got funny ones, and some people had, sweet ones, but it was always very nice of people to do. Very kind of you, Annabelle.
Give out the cards to like, everywhere we go to everyone,
Mm-hmm.
but this time it got too late and I didn't have time to do cards for like 25.
That's a lot of people. Yeah, that's a lot of people.
Like,
Yeah, I don't know why these lights won't turn on. It's really weird. Alexa, turn the living room on. The ceiling lights
Those di-
are supposed to turn on and they're not. I don't know. We're just gonna have, it's a sleepy day. We'll try to wake up in class.
the dinosaurs were made with 3D printers.
Oh, really? Did you do it yourself? Wow. That's incredibly cool. Very cool of you. It's really cool.
Yeah, most of them have the dinosaurs, but some of them don't.
That's really sweet of you. All right, well, let's see. I don't see Lucy yet, but PJ woke up sick. Oops, I'm gonna have to take one more out for PJ. I just got a text from her mom. PJ woke up sick. I'm scanning this a minute. Hope she feels better. All right. Well, we'll go ahead and get started. I think Lucy's still coming. I haven't heard that she's not. So, all right. So today we're going to talk about acid bases and solutions. Thank you everybody for bearing with me last week. I don't think you wanted my crud. By by Tuesday I felt better, but you know, the rule is if you have a fever or if you've got stuff spewing out of any orifice, you probably should give yourself 24 hours before you're around other people. And I had a fever Monday morning when I woke up. So I was like,
But you didn't have
Yeah.
anything spewing?
no, thank gosh, I didn't throw up or have diarrhea or anything gross like that. I just had a fever. Yeah, it's just a fever. Yeah. Yeah, it was just a little fever. It wasn't too bad either, but I felt really tired for like 4 days. I just wanted to sleep, but that's okay. But yeah, so I still have like a little bit of a cough, but it's not contagious.
There are very. I like the birds that come near your bird feeder.
Yeah, they're fun. There are lots of, I post them on my Facebook and Instagram all the time because I post pictures and videos of them. I get good ones. They're fun. I like my birds. Okay, so thanks everybody for last week. We're actually gonna have time today in lab. Today's lab was a shorter lab, so we're gonna have time today to do both the demo from last week that I wanted to show you, which is super fun. And also, if you want to do last week's chromatography lab just for fun, you should have time in your lab team today to do it, just to kind of see it happen, because it's fun to watch. Even if you don't collect the data or anything, it's just fun to watch. All right. So we're going to talk about acids, bases, and solutions. We talked about solutions last week or week before last, whatever, different kinds of solutions, things like that. Now we're going to talk about acids and bases. And for the next couple weeks, we're going to be doing, today's lab is about reactions that are reversible. So a lot of reactions, not all, but a lot of reactions are reversible. And so you can go from reactions to products and then back to reactants again. And that's what we'll be doing in lab today. And then after that, we're going to get into a whole series of labs that have to do with acids and bases. And you'll be like neutralizing acids or neutralizing bases. And you're going to see a lot of color change in lab because we're going to be using indicators that allow you to see color change. And they're really fun labs the next couple weeks. All right, so let's talk about our properties of solutions. A solution is a homogeneous mixture, which means what? What does that mean?
It means it's a mixture that can't be something.
Yeah, it can, but yeah, you have to filter and stuff. Yeah, all the particles are so small and evenly dispersed that you can't just easily separate them mechanically, not easily. Yeah, that's a good one. Yeah, like salt water, that kind of thing, solution. Homogeneous mixture. A solution is composed of one phase. So a solution exists in one phase. Either it's a solid, a liquid, gas, right? You can have solutions that are in each different kinds of solutions can exist in each different phase, but a solution is always in one phase. The particles are not visible to the naked eye. A solution does not scatter a beam of light. So if I were to shoot a beam of light through a tank of salt water, that it wouldn't scatter, it wouldn't cause the whole tank to light up, right? But there are some things that will scatter a beam of light, and you'll see like the whole thing will refract the light. A whole container would light up, for example. And then components of a solution cannot be separated using simple mechanical filtration. Yeah. Oh, you're gonna answer the first one? Okay, so what's dissolved, Eunice?
Solid.
A solid. And then Annabelle, what does the dissolving?
Solvent.
Solvent, very good. So there are some solvents that you use all the time as part of your daily life. There are solvents like WD-40 is actually a solvent. People will use it to like loosen locks and stuff, but that's not really what it's for. Watering is called a universal solvent. It dissolves all kinds of things. And then you can also, like if you've ever had Halloween makeup that's oil-based and you needed baby oil or lotion to take it off, that's also in that case a solvent. So let's see. Anybody have any example? There's lots of examples. But gas solution, gas dissolved in gas. Anybody want to,
Carbon dioxide.
Carbon dioxide is a compound.
Carbon dioxide. Air.
You just said air. You just said air. Air's your answer. Air's a perfect example of a gas solution. You got nitrogen and oxygen and carbon dioxide primarily in your air. You got other stuff, but those are the big ones. Okay, Annabelle, what's a gas liquid? Vapor. Okay, that's her example. Maybe.
Carbon dioxide. Vinegar.
Vinegar. So how about carbon dioxide in soda? That's a great example. And okay, let me ask you about fish. Anybody have a pet fish?
No,
Mine's gone. I got a dead one now, so I don't have one at the moment, but I usually have a little fish sitting right here. It's just this year I lost mine.
I used to have one.
So what do fish, do fish use respiration? Do they breathe?
They breathe using their gills.
Their gills. They breathe using their gills. What are they breathing in?
In carbon dioxide.
They're breathing in oxygen, just
they're
like
breathing in
you.
Oxygen. That's
But
why
they're bringing in oxygen that's dissolved in the water. So
that's why you need
they,
to have special water for.
yeah, well, usually that has to do with the chemicals in the water, but yeah, that there's oxygen and other types of gas, but there's oxygen dissolved in water, and the fish's gills have the ability to pull those oxygen molecules out of the water. So yeah, there's gas dissolved in regular water too, but your carbon dioxide in your soda is a great example, because when you open a soda, what's the first thing you hear? Yes, right? That's because you're releasing the pressure, so now that gas is coming out of solution. How about gas solid? This one's harder, do you know?
Dryers.
That is gas in solid form, but an example of solution would be, so when they want to store hydrogen gas, one way to store hydrogen gas is actually to dissolve it in palladium metal. Isn't that interesting? Because remember, hydrogen's really flammable, right? Like a tank of hydrogen is full of very flammable gas, usually under pressure. Yeah. So you can actually store hydrogen gas in palladium metal. That's one way they store it, is in solution in palladium metal, and then they can remove it when they need it. Interesting, right? Liquid. Anybody know? What do you think?
H2O.
H2O is a compound. What's an example of one liquid dissolved in another liquid? Do you know? Get an idea?
Vinegar.
That's acetic acid. So gasoline's an example. You have different, remember you usually have like ethanol in gasoline, and then, yeah, ethanol is like an alcohol. And then you also have petroleum distilled down to gasoline, right? So those are two different things, but they're dissolved in one another. You know the numbers on the gas pumps? You ever seen it? Usually it says like 87, 89, 93. That tells you how much ethanol is in your gasoline. So how much alcohol. It's a rating for how much alcohol. All right, solid dissolved in a liquid. This one's much easier. We think of this kind of stuff all the time. What do you, anybody, one of you girls, Emerson? Salt water, it's a great example, or sugar and water, great example. Okay, how about a liquid dissolved in a solid?
Liquid dissolved in a solid.
It's harder to think of. How about mercury and dental amalgam? Okay, now this is interesting. Mercury, what's mercury's state at room temperature?
Ready. I'm kidding.
It's a liquid at room temperature, right?
I was joking with
Yeah,
the
you're
friend.
It's a liquid, right?
It's used to measure.
It can be in mercury thermometers, yes. But mercury is used in dental amalgam. Okay, anybody have or know anybody who has what they call silver fillings in their teeth? Yeah, they're not actually silver. It's actually mercury with copper and a couple other things. Now, mercury, this is interesting. Typically, mercury is highly toxic to humans. It can cause neurological damage. But in dental amalgam, in solution, it's usually completely safe. Which is interesting because when it's not in solution, it's not safe. So, and we're going to talk a little bit about in just a second about mercury and what happens if you get exposed to mercury. But a lot more commonly now, you see what are called composite fillings, and those are the tooth colored ones, the white ones that look like your teeth. That it's hard to see, then you have to like really look closely. But like when I was a kid growing up, it was all dental amalgam, which is the mixture, the solution of mercury and other things. And I had a dentist tell me once, and this was really smart. If you get the silver fillings, the amalgam fillings, in time, they have to remove and replace them because they get loose, but also because they're a different density than your teeth, and they behave differently than your teeth. So, You know what an awl is for chopping wood? It's like this little triangular wedge that you drive into a piece of wood and then you hit it with a big hammer and it eventually splits the wood open. You ever seen that? So an owl, it's a little like a wedge and you tap it into a tree piece of wood and then you swing a big hammer or the backside of an axe and it splits it. Well, that's what amalgam fillings do to your teeth over time. They will crack your teeth. And I had a dentist tell me once that the best thing, what do you think might be the best filling? Best material for filling? Gold. Because it's inert, so it doesn't react with anything. People aren't allergic to it.
But it's costly.
It's very costly, but it also wears down at the same rate as your teeth do. So it works more naturally with your body, but most people can't afford it. And then a good example of a solid would be like sterling silver or brass or any kind of metal alloy. That would be a good example. All right, so why did what did I just say about dental amalgam having mercury and mercury being bad for you? Anybody familiar with Alice in Wonderland or Alice Through the Looking Glass? Who's the guy that hosts the tea party?
The Mad Hatter.
The Mad Hatter. What is a Mad Hatter? What is that? That is based on something very real, the character the Mad Hatter. So here's why, and it's pretty crazy history. Probably got a commercial. Ooh, that was yummy.
Eat smart.
Yay. Okay.
This episode is sponsored by Wix.
Good for
Go to
Wix.
wix.com/go/simple history to create a website today. Dangerous jobs in history. Hat maker. When you think of a dangerous job in history, you might think of the occupation of a soldier or someone who dealt with disease, like a plague doctor. But you would not think that hat making would be so dangerous. In the 1500s, the milliner became a term to describe a trader that specialized in importing women's accessories from Milan. As hats began to become a popular status symbol for men around the 14th century, by the 17th century, mass production of these fashion items became necessary to meet the growing demands of Western society. Being a milliner became a lucrative business to be a part of, and the variety of materials used by hat makers bred experimentation in style and production. It was soon discovered that moistening the fibers of felt and fur with mercuric nitrate created a superior material that could also be made quickly. This development in hat making was supposedly discovered by a French milliner being treated for syphilis with mercury, who used his own urine to separate the animal's fur from its skin.
Gross.
By the 19th century, it was already common practice to use the mercury compound in manufacturing. Called carroting, the process involved washing fur in an orange-colored solution containing mercurial nitrate. While the use of the substance made matting and removing the fur from the pelt much easier, long-term exposure to the vapors released from the liquid could develop into a serious health condition called erethism. Because mercury attacks the nervous system, symptoms of erethism are both psychological and physical in nature. Mentally, it initially manifests as a struggle to control one's emotions, high levels of social anxiety, and an inability to think or speak clearly. As the body's motor functions begin to break down, severe tremors, a stumbling gait, and drooling would make many people mistake the sickness for drunkenness. In extreme cases, the inflicted will be beset by hallucinations, delirium, and extreme paranoia. As the associations between milliners and the symptoms of erethism became evident, it is believed that the term Mad Hatter and Mad as a Hatter came to be used to describe this particular type of psychosis. Hatter's shakes became a term to describe the intense muscle spasms and tremors seen in workers of the trade. Near the end of the 19th century, the dangers of mercury poisoning in the profession of millinery began to be studied by the French Academy of Medicine. By 1874, alternatives had been developed to replace mercurial nitrate, and by the turn of the century, laws in England and France were enacted to protect the workers in hat manufacturing. Unfortunately, mercury poisoning would nonetheless continue to plague milliners in the first half of the 20th century. The United States had developed an alternative method by using hydrochloride, but the poisonous mercury compound would be used up until the early part of the Second World War. Mercury was a key material in detonators for explosives, and the needs of the war forced American millinery manufacturers to finally adopt the new processes already developed. In 1941, Millineries in the United States finally agreed to use hydrogen peroxide instead of mercurial nitrate. Millinery as a craft began to be slowly phased out through the development of new technologies and methods in industry. And with the cultural attitudes that emerged from the wars in the 50s and 60s, hats no longer were the symbol of status they once were. The making of everyday products was a laborious and often dangerous affair before modern industry, and hats were no different. Lewis Carroll's character in Alice in Wonderland, the Hatter, exhibits many of the traits of erethism, but he may have been inspired by a furniture dealer that was colloquially called the Mad Hatter because of his eccentric personality. Nonetheless, this expression was commonly used by Carroll's time, and the implications between hat making and psychosis had already made its way into everyday vocabulary. Whether intentional or not, the title preserves the memory of what was once a grim and dangerous job, the job of the hat maker. Don't be a Mad Hatter. Use wigs to build your dream website.
Did you catch what they said as the mercurial, the first source of mercurial nitrate?
Wix has great features to bring your site to life, such as Wix Videos, Wix Pro Gallery, Wix Bookings, and solutions for all
But
kinds
did
of
you hear what they
sites,
said
such as
was
e-commerce,
the
music,
the
hotels,
likely,
events,
oh,
restaurants,
stop.
and more.
Gosh. Did you hear what they said was, oops, why did it just do that? Was likely the first source of mercurial nitrate for hat making?
Simple hit.
Why are you doing that? Move on, move on. Thank you.
The camera
So,
is down.
did you hear what they said?
The camera's down here. You're.
It's okay. Yeah. So, actually it shows it almost everybody. So what they said is there was a hat maker who was being treated for syphilis with mercury, a drug containing mercury. And then therefore he used his own urine to help separate hair from pelts for hat making, because he was releasing the mercury from his body in his urine, and it turned into mercurial nitrate because nitrogen is in urine, ammonia is in urine, there's nitrogen in urine, and it created mercurial nitrate in his body and got released in his urine, and then he used that to help make his hats. Oh. Yeah. Oh yeah? How's it go?
What she thought was H2O is H2SO4.
Oh goodness, you don't want that.
What is H2SO4?
Sulfuric acid. All right, so acids and bases. Let's see. So acids turn blue litmus paper. What color? Emerson. Red. And then bases turn red litmus paper. Everly? Blue. Very good. All right. So we have litmus paper. I've actually got this is a little antique containers of red and blue litmus paper right up here. See them? Ooh, they're cool. But yep, they will change color. That's an indicator, a pH indicator that will give us a color change. All right, acids give off H+ ions. What kind of ions are those, Annabelle? What's an H+ ion? Yeah, but what is it? H is, hang on, Annabelle.
Hydrogen.
Hydrogen ions. Very good. And bases give off OH negative. What's that? Do you know, Eunice? This is hydroxide. So anytime you hear something hydroxide, that means it's a base, first of all. So sometimes you'll hear like sodium hydroxide or something like that. You'll hear that used. All right, acids generally taste how, Everly? Sour. And that's because that positive hydrogen ion is what produces that taste. And what do bases taste like, Emerson? They're bitter. That's right. So bases are bitter, and that's because the hydroxide ion, but they may have other tastes, and that can depend on the other parts of the molecule. What else is going on in that molecule? Acids corrode what? Do we know what it means to corrode? So metals, corrosion in metal is the breakdown of the metal itself. Acids will break down metals. They will corrode metals. And bases denature. Do we know, Emerson? Yep. proteins, though, is what we're looking for. So denaturing a protein, we're gonna look at what that looks like in a minute, but denaturing a protein is proteins are big, long molecules that are folded up like a fan, like little fans that you go, now they're folded up. That's how proteins behave. Denaturing them is when you go in and you start messing with the molecule and breaking it down, and it unfolds and parts of it come detached. That's denaturing a protein. And that's what your body does when you digest proteins, is it denatures some of them and breaks down others into amino acids. So bases will denature. Acids have a pH greater or lower than 7. What do we think? Do you know? Yeah, acids are less than 7, and pHs are usually what in nature? Do we know what this one is? So this is soapy or slippery. Bases tend to be soapy or slippery. And pH on a base is going to be what, Everly? Higher than 7. Okay, so acids are lower than 7. pH on bases is higher than 7. So if it's 7, we call it neutral, right? 7 is neutral. All right, this one's a quick video. Just compare a couple things here with acids and bases from a chemical perspective.
About snow. And you it's time to talk. with-
Georgia, natural gas, yes.
What is a base in chemistry? Let's start with the difference between an acid and a base. The acidity of a solution is measured by its number of hydrogen ions. You can look up this measure on a pH scale. The abbreviation pH stands for potential hydrogen, and it's a measure of how much hydrogen is in the solution and how active that hydrogen ion is. Hydrogen ions determine whether a solution is an acid or a base. A base that is water soluble is called alkali. Acids are hydrogen
Get it?
ion donors,
Yeah.
and alkalis are hydrogen receptors. A substance with a pH lower than 7 is considered acidic, and greater than 7 is an alkaline. 7 is neutral. Each interval on the pH scale is a 10-fold increase. So a solution with a pH of 5 is 10 times more acidic than an object with a pH of 6. The difference between an acid and a base comes down to the number of positively charged hydrogen ions. When an acidic substance is dissolved in water, it releases hydrogen ions, causing an increased proportion of positively charged hydrogen. When an alkali substance is dissolved in water, it releases negatively charged particles called hydroxide ions. Remember, an alkali is a base that is water soluble. Again, acids are called hydrogen ion donors, and bases are hydrogen ion receptors. Let's look at a couple of characteristics of acids. Acids taste sour. Acids turn blue litmus paper red. Acidic solutions have a pH less than 7. Characteristics of bases. Bases taste bitter. They feel slippery. Bases turn red litmus paper blue. And basic solutions have a pH greater than 7. Acids typically have a hydrogen in front of it with their chemical formula. HCl is hydrochloric acid. HF is hydrofluoric acid. And bases typically have a hydroxide ion. NaOH is sodium hydroxide and is a base. And KOH is potassium hydroxide and is also a base. Hope that was helpful. Thanks for watching. And remember, time is multiplied.
So acids are hydrogen ion donors because they have hydrogen ions to give away, and bases are hydrogen ion acceptors because they have OH negative. What happens if you put an H plus and an OH negative together?
They form neutral.
And what does it form? What is H plus and OH negative? If you water. If you have an H plus and an OH negative and you put them together, are you going to get water? And the signs are going to cancel out. So you're going to have neutral water. That's why a chemical reaction where you have an acid and a base put together and they neutralize each other, you're always going to get a gas, a salt, and water. That's where your water is going to come from. Okay, let's see.
Well,
Where'd the dog go? So similarities, when you dissolve an acid or a base in water, it makes what?
Mixed gas.
It makes what I said, 3 things it makes. I get salt, which, or ions, right? Which, that's where you're getting the, it makes ions, sorry. But when you put them together, you get salt. You remember how salt is an ionic compound? So if you put an acid or a base in water, you're gonna get the ions, and it's either the OH negative ions if it's a base, the H plus ions if it's an acid. And then remember, when you put salts in water, they dissolve into their constituent ions, and that makes them conductors, right? Okay, so same reason that acids and bases are conductors, because when you put them in, they have ions, right? They have either H plus or OH negative ions. So just like when you put salts or other ionic compounds and you dissolve them in water, and they produce free ions to conduct, same thing happens with acids and bases. The stronger the acid or the base, the more ions that are produced, the better the conductivity. So like very strong hydrochloric acid is going to conduct electricity better than very weak hydrochloric acid. They can both conduct electricity, both acids and bases. That's Lucy's. I'll make sure she gets it.
Hey,
When
well,
it-
I think Lucy's right over there.
She is? Well, hang on, she'll come. Well, I'm gonna keep going. So when an acid reacts with a base, what's formed, we said?
Neutral.
Well, this salt, that's what we were saying before, yeah. And they both carry and share ions. Here, Annabelle, I'll take it. And I'll make sure she gets it. You sit back down though, okay? So you don't miss any lesson. There you are. Oh, well, here, this is for you. That's from Annabelle.
Thanks, Sarah.
Yeah, there you go. Go have you a seat. Okay, so let's see, what else do we have here? So now we're gonna play acid or base. Let's see. All right, let's take a vote. Who votes for milk being an acid and who votes for it being a base? Okay, hands up for acid. Hands up for base. And let's see. It's an acid. Milk has a pH of less than 7. How about wasp venom? Who says it's an acid? Who says it's a base? It's a base. Wasp venom is a base. I'm allergic to wasp venom. I have an EpiPen for wasp venom. Oh boy, am I allergic to wasp venom. All right, bleach. What now? What is? Bee stings. Yep, they're all kind of the same for me. Yep, they're not good. Yep, yellow jackets got me on I stepped on one when it was barefoot. It got into the house and I stepped on it barefoot. And the bottom of my foot has lost like all sensation. I got permanent neuropathy where it stung me because it destroyed all the nerves in my foot. Like they're dead for good. All right, bleach. Is bleach an acid or a base? Who says it's an acid? Who says it's a base? Bleach is a base. How about a mango? Is a mango acidic or basic? Who says? Yeah, but is it acidic? Who says acid for mango? Who says base? It's going to be an acid. How about vinegar? That one's easy. Acid or base? Acid? Everybody knows vinegar's an acid. How about lye? Do we know what lye is? They use lye in old school soap a lot of the time.
You're lying.
Yeah, lye is different, but lye can burn your skin. Is lye an acid? Who says yes? Is it a base?
Acid.
It's a base. Now how about an apple? A good old apple. Is an apple going to be acidic or basic? Who says it's acidic? And who says basic? It's acidic. Well, think about it. You make vinegar from it. Kind of makes sense. Now, how about spinach? Who says acid for spinach? Who says base? Do you remember it said that bases can be slimy or soapy? Spinach can get slimy. Like when you're working with it, it can get a little slimy. There you go. Okay. Pineapple. Yeah, you say acid? Anybody agree with him? Yeah, it's going to be an acid. How about soda?
Soda is an acid.
Who says acid? Yeah, everybody says acid. Okay, here's an important thing to remember about soda. So even if you drink diet soda with no sugar in it, it can still cause you to get cavities because there's an acid, there's carbonic acid in soda. Oh, yes. Yes.
Good thing I
So
don't drink much of it.
there you go. So if
I
you
don't
have
know none.
carbonic acid, which comes from the dissolved carbon dioxide in the water, in the soda, it has acid in it, and that acid can eat at your tooth enamel along with your saliva, and it can cause cavities, even if there's no sugar in it.
Wait,
Okay. Uh-huh.
So the bases are the slippery ones, right?
Tend to be. Yep. So what do you think hand soap is?
Base.
A base. Good one. How about a lime? How about a lime? We think lime is an acid? Yeah, lime is an acid, just like a lemon. Yeah, very sour. All right. How about? Oh, I'll wait for you girls. Are you girls paying attention? Let's focus back over here. How about baking soda? That's a base, right? Because you put baking soda and vinegar together. Everybody's seen that. Window cleaner. Base, acid. So it depends on what kind of window cleaner you're using. In this case, what they're talking about is like Windex, which
Okay,
tends to
that's a
have
base.
ammonia in it, and that's a base. But if you are like me, like I make my own cleaners usually because it's less expensive and I think they do better. But like my glass cleaner is vinegar and water and like 1 drop of soap, dish soap. And that makes like the best glass cleaner. So that's actually acidic, but yeah.
I think that stomach juice is an acid and drain cleaner is a base.
Okay, so stomach juice is definitely an acid, and drain cleaner is typically a base. Typically, your drain cleaner very often is a sodium hydroxide situation. Not always, but like a lot of them have, some of them have acids in them, but a lot of them are just very strong bases. Your stomach is full of hydrochloric acid, which you're going to use in lab today. And it's full of very, very, very strong acid with a very low pH. But the lining of your stomach is special in that it doesn't get burned by its own acid. Whereas if you throw up, does it make your throat burn sometimes?
Yeah.
That's the stomach acid, right? It's terrible. Or sometimes you'll have a baby that gets sick, and if a baby gets sick and has like a diaper blowout, sometimes there's enough stomach acid in there, it can burn their little bottoms, and they get little burns on their bottom.
Let's,
Awful.
I've always
please,
heard that if you pour your stomach acid in a glass cup, it'll break.
Miss Danny,
Usually not glass, but some things.
do you know what a metaphobia is?
A metaphobia?
Google it.
Not right now. Can you tell me though?
I think it's the fear of throwing up, and it's like,
I don't like throwing up.
And I haven't
I don't-
really.
Throwing up is like the worst. Okay, let's watch this quick one here on what are acids. We just did what were bases a minute ago.
So.
And yeah, 2, 1. Harbor Freight.
When I was a kid, I had this mild fear that one day in a sinister evil laboratory, a mad scientist concocted a super acid would one day accidentally spill it on the floor, and it would begin its long journey of eating through the earth. This is, of course, not possible. The chemical world may have different rules than our world, but it still yearns for the same thing: stability. The reason it's easier to sit rather than stand is the same reason wood burns and metal corrodes. The end result is more stable and takes less energy than the initial state. Basically, just like us, if chemicals have the opportunity to make their lives more easy or stable, they'll take it. But what dictates the stability of the chemical world? The stability of a molecule relies on the strength or energy within the bonds holding it together. These bonds are formed from electrostatic attraction between protons and electrons. And just like with magnets, this attraction gets stronger the closer they are together. Molecules are most stable when all the electrons are as close to as many protons as they can be. However, there are a ton of factors or rules that dictate how close electrons can be to specific nuclei atoms. The most important of these factors is called electronegativity. As an atom increases in size, it also increases the number of electrons orbiting around it. Because electrons have like charges, they don't like to be near each other. If enough electrons begin orbiting our nucleus, eventually the attraction of the nucleus isn't worth the repulsion of all these electrons, at which point new electrons start accumulating in another outer shell. This is important because now every new electron that is added not only feels the attraction of the protons in the nucleus, but also the repulsion of the electrons in between them. Electronegativity can be thought as the ratio between protons in the nucleus and the electron shells underneath the valence shell. It's not exact, but it fits pretty well. This means that these elements have higher proton to electron shell ratios, meaning electrons, if given a choice, would prefer to spend their time here. So then, what are acids? For this, I'm going to stick to the most common and most prevalent description of acids and their behavior. The Bronsted-Lowry description states that an acid is a molecule that can donate a proton or hydrogen atom. What does that mean? An acid is a naturally unstable molecule. The more unstable it is, the more acidic or corrosive it is. Just like you and me, acids don't want to be unstable or unhappy. So if given the opportunity, they'll react with something to change that. But why are acids unstable? If we look at the most common or abundant acids, we see a trend: a hydrogen atom bonded to an electronegative atom. Now remember, electrons want to be as close to as many protons as they can be. That's how we form the most stable molecule. So if we imagine the point of view of these electrons bound to the hydrogen, they may be thinking something along the lines of, why am I hanging out with this loser? Just give me any excuse to ditch this guy so I can go hang out with all those Chad protons over there. But these electrons have a responsibility to hang out with Harold Hydrogen, and they can't ditch him for no reason. So this bond isn't very strong. However, if another molecule shows up with another pair of electrons to hang out with Harold, then these electrons will go, oh, hey, have you met Harold? He's really great. Well, he's your problem now. Bye. That's essentially what acids do. They exist in a constant state of instability, always looking for a lone electron pair to pawn off their extra hydrogen to stabilize themselves. If the person they can pawn off their hydrogen to is more stable with it than the acid, well, then they do it. Hence, strong acids are very unstable and can force almost anyone to take their hydrogens. Additionally, a single molecule of acid can only burn another single molecule. So that's why acids don't just keep burning through the earth. Eventually, it runs out of protons to give. But why do acids burn us? A chemical and thermal burn produce the same result. They destroy proteins. Proteins are the most important biological molecules in our bodies. They do essentially everything that keeps you alive. The reason they can do these things is because they are perfectly and exactly folded in a very precise shape. This shape is maintained by intermolecular forces and interactions, the strongest of which are salt bridges and hydrogen bonds. Now, I won't go super chemistry on you, but every amino acid, the things that make proteins, has a carboxyl, which is the acid part of amino acid. But in proteins, the carboxyl group is often missing its acidic hydrogen, and thus has an abundance of electrons and a negative charge. This negative charge can then bond ionically to an amine ion of another amino acid, or hydrogen bond with an alcohol of some other amino acid. These interactions play an important role in keeping a protein folded together. However, if we introduce an acid, this abundance of electrons on the carboxylate ion is a prime location to unload the acidic proton. So this carboxylate ion receives the acidic proton, becomes a simple carboxyl group, and loses its negative charge. If enough acid reacts with enough ions, the forces holding the protein together will fail, and it will unfold into a new shape. Without its original shape, it can no longer do its job. And if enough proteins become corrupted, then the cell becomes a useless mass of organic tissue, a burn. Bases do the same thing, but in a different manner. Instead of donating a proton to the carboxylate ion, they rip a proton from the amine ion. However, unlike acids, most bases have a hydroxyl group that will turn into water after the reaction. This water can then work with the base to start hydrolyzing or splitting other organic bonds via alkaline hydrolysis. So theoretically, if you needed to dispose of a body, A strong base is the better option as it will be a little faster for dissolving some components. Lastly, how can we store these caustic substances in simple plastic containers? Well, remember, it's all about the electron's happiness. The simplest plastic, polyethylene, just looks like this. Now, if you were an acid, there's no free electrons to take Harold away from you. You'd have to rip apart a bond to get rid of Harold, which is possible, but only by the absolute strongest of acids, and if given some heat energy to help loosen up those bonds. The same thing happens with bases. None of these electrons would be happy giving up their proton for the base, so there's no reaction. Thus, almost all acids and bases don't eat through plastic, but have no issue burning us.
Okay, so why did it do that? Yes, yep, you need to get rid of a body. You can always do a base. Actually, this may be a little morbid, but come here, go to the next page. Our last dog, instead of burying him, well, we ended up burying him, but one of our options was something they call, why is it doing this to me? It is stuck. A process they call aquamation, which is basically dissolving the dog. Oh, come on. There we go. Dissolving the dog in a very strong base liquid bath, and it makes like cremains, but you don't use fire. Instead of using fire and heat, they use the base to dissolve the little organic matter down to powder. Okay, real quick, we're going to wrap up here. We only have about 2 minutes left. So your common acids and bases, here's some on a pH scale. This gives you the pH number. So battery acid, you see down here at 0, that's very strong acid. And over here, you got oven cleaner as a very strong base and all sorts of things in between. If you notice, you can eat a lemon. That's way down here at 2. And you can also, like, here's egg white is all the way up here at 9. Your body can actually handle a fair amount of pH fluctuation and do all right. So when found in foods, I'm just going to give you these because we don't really have time to call. All right, so when found in foods, acids taste sour. When found in foods, bases taste bitter. Compare how an acid and a base will react with the metals, magnesium, zinc, and iron. So an acid is corrosive to magnesium, zinc, and iron, because remember, acids are corrosive to metals. It wears them away and produces bubbles of hydrogen gas. A base does not react with metals. Compare how an acid and a base will react with carbonate ions. A base would not react, but an acid would produce carbonate ions. What color does acid turn litmus paper? Red. What color does base turn litmus paper? Blue. And what's neutralization? This is a chemical reaction in which acids and bases are added together and they quote unquote deactivate one another. They drop your pH to neutral. Corrosive is a substance that can wear away certain materials, and an indicator is a substance that changes color in the presence of an acid or a base. So compare and contrast acids and bases. How are they alike and how are they different? So somebody give me an acid, somebody compare an acid and a base, meaning tell me how they're alike.
They're alike by reacting.
Yeah, they can react with each other. How about, can they both burn you? Yeah, okay, excellent. How about they're different? Which one donates hydrogen?
Base.
Protons. Donates a proton or a hydrogen H plus. That would be an acid. And what receives an H plus? That's a base, right? Okay, very good.
And the acids react with metals.
Acids react with metals. Yes, very good.
French fashion.
Okay. Let's get ready for that.